Today, we're going to speak about steam. I guess you can figure that out. It says steam management here. We're going to speak to a couple of folks from steam management, James and Chase. The reason why I think steam is important, well, one thing is it's important to know this and to actually hear about steam over and over and over again, especially for those of us who aren't experts, because this is kind of hard to sink into your minds how this works if you don't think about steam every day. So I think it's really valuable. The reason why I think it's valuable for M&V people is that some of your projects do have, steam boilers and steam systems, and there might be something wrong with, the system. And it would be nice if, when you're doing your routine visits to the site to make sure things are working right, if you would notice something, it's like, hey, that doesn't seem right. I remember I saw that webinar on steam and they said that I should look for this. And this is kind of funny. And so you might actually be able to find some pretty good little projects that might be low payback that could save them a lot of money. That's the value of sitting in on this webinar. It can help you in your job to do it a lot better. Anyway, that's it. I'm not going to introduce who James and Chase are. They're going to do it themselves. But let's get going.
Thank you, John. This is James Moore with Steam Management. With me, I've got Chase Dean and Keith Carlson, who couldn't attend today, and Jason Steeney, who is with us in silent. Thank you. Next slide. Bit about Steam Management. We're a turnkey solution provider. We do design, bid, build services. A little more about Steam Management is, next slide, please. We work in C&I, utilities, healthcare, higher ed, federal, and municipal markets. And today's topic presentation is Beyond the Steam Trap, a holistic approach to achieving and maintaining steam system efficiency. And this technical presentation will include some information that will go into a deeper dive. Talking about Beyond the Steam Trap and steam system efficiency, we expect the audience to gain an understanding around the focus, typical steam system opportunities, energy opportunities, and then we want to do a deeper dive into some of those opportunities for you with an overview, key indicators, efficiency solutions, and examples, including calculations. Today, we're going to start by talking very briefly about an audit process, which most of you are all too familiar with, and the audit levels. And these are a little bit different when we're talking about steam systems on a holistic level and looking at especially industrial and energy audits for utility providers. Chase is going to take the discussion over from here.
Yeah, thanks, Jamie. So I'm just going to quickly go through the audit process. I'm not going to go through these line by line, but yeah, your first step is organizing the assessment. So this is like your pre-audit work, data gathering, communicating the audit plan, and getting stakeholder buy-in on the plan. And then you go to conducting the assessment. So this is the actual on-site assessment where you are gathering data, interviewing stakeholders, identifying potential opportunities, those kind of activities. Then you go to the assessment data analysis. This is kind of like your computer simulation stage where you're quantifying opportunities, identifying which ones make sense, and meet the energy and financial goals. And the important takeaway here, particularly with steam systems, is to develop the heat and mass balance, which we'll show on this slide. So here's an example of a preliminary heat mass balance for an ongoing project that we're working on for the near mill. So we took an old flow diagram from the plant, identified relevant operating points, and created, you can't see the data points here, but we have process data for each of these identified operating points, and basically balance everything out based on the steam and mass flows, or the mass and heat flows, and are able to kind of make sense of the system. And then from there, run additional cases. And this is important because we're able to use this to really understand the system, but also we can throw in a piece of equipment here, adjust the balance, and kind of help identify potential opportunities. And then last but not least is the audit report, which I'm sure you're all familiar with, but this is just where you detail the findings of the audit and recommendations. As far as audit levels, level 1 is your walkthrough audit or proposal assessment. This is to identify what opportunities are available from a high level. Level 2 is the standard audit, and the goal here is to get to a 60% design and stakeholder buy-in to go into detailed design. And then level 3 is investment grade audit, where we're either generating a full engineering package or we are generating a full engineering package for a design build or design bid.
Most of these levels, when you start at level 2, you start to look at automation, process and system automation, and this is where it's really important that you understand the heat and mass balance, as well as being able to get to a 60% design with buy-in. So that's where that high level 1 walkthrough is so important, because it helps you identify those opportunities before you start to put real effort into what you're going to design on a steam system.
Yeah, so for the purposes of the presentation, we kind of talked through the system in 4 parts, and the opportunities it was separated into 4 parts. So we have generation, distribution, end use, and recovery. I'm going to go through those on the next slide here. So generation is your all the equipment in your boiler room, your boiler feed water pumps, deaerator, etc. Distribution would be your steam piping and your traps. End use is your steam users, your process heaters, heat exchangers, steam consumers, etc. And then recovery is your condensate collection tanks, pumps, and return piping. And so we've broken down the opportunities this way, but you should note that, it's very easy to have a distribution or a recovery opportunity within your boiler house. It's just, we split it up this way. So for generation opportunities, the examples we're going to run through are boiler blowdown heat recovery, blowdown control upgrades, burner combustion optimization, and economizer / combustion air preheaters. Other opportunities that we're not detailing but are still common opportunities are minimizing short cycling losses, optimizing the aerator, burner upgrades or repairs, adding or restoring boiler refractory, improving water treatment, implementing a combined heat and power or cogen project, mechanical drive turbines, so like steam driven turbine, or converting a steam driven turbine to an electric motor, and then boiler replacements or cleaning boiler heat transfer surfaces. So that could be on the flue gas side or the water side. You get any kind of buildup on those surfaces, and that's decreasing your boiler efficiency. So the first one we're going to run through is boiler blowdown heat recovery. So on most boilers, you have what's called surface blowdown, which is boiler water flow out of the steam drum that removes impurities from the boiler. This is mainly dissolved solids. And that blowdown water is at saturated temperature. It's directly from the boiler steam drum. So as that flows out of the boiler, all this heat is literally just being blown down the drain. And this rate's usually around 2 to 8% on a boiler. I have seen it up to 20% in the field. So this is that's 20% of the boiler output. So this is a lot of heat being wasted if you're not, capturing heat from it and cooling it down before it goes to drain. Recovery skid or something like this, but so you can see, let me pull my pointer out here. So you have your input
Chase.
here. So yeah.
Chase, this is John Avina. Hey, can you change your mic again? Sorry, we're starting
Sure.
to get some interference or something. Thank you.
So here you have your blowdown line coming in into a flash tank here. You're flashing off steam, which can then be used, and this is clean steam, even though you have dirty blowdown coming in. The flash steam leaves behind those impurities just like they build up in the steam drum. So you can put this steam into your deaerator. That's probably the most common application. Or if you just have any low pressure steam users, you're able to reuse that steam. So then in the flash drum, you have your drain coming out that goes through a steam trap and then flows through a heat exchanger. And anything you can send through that heat exchanger to kind of capture that heat, you are able to do that. And in this case, we have makeup water. So that's water going into the deaerator to be used in the boiler. So this is the boiler blowdown control upgrade. So this is basically using a digital controller to modulate blowdown. And this is an opportunity for either two configurations. So you have your manual blowdown. This is blowing down the surface water by just basically an operator going out periodically and opening a valve and blowing the boiler down until the samples are coming out to an acceptable TDS level. So there's a kind of an intermittent manual method of doing it. And then continuous blowdown is still a manual method, but you have a control valve. It has set points on it. And so periodically you're going out and adjusting that valve, but it is continuously blowing down. And so there's still some waste there because you have to be conservative on that set point to keep your boiler, at an acceptable TDS level. So the solution here is to install a closed loop digitally controlled blowdown system. So you have a sensor here that is measuring conductivity in the steam drum. The total dissolved solids are basically metals. So as they build up, your conductivity in the water goes up, and that's what we're measuring. And then that goes to this controller, which modulates the blowdown valve. So you're just continuously controlling that blowdown flow and keeping it right at your desired TDS level. And so you're really optimizing how much blowdown you have to use and reducing waste that way. So for the example project here, this is actually a combination of the heat recovery and the controls upgrade. This is for a specialty paper company we worked at in New England, and this is a boiler operating at 150 pounds, and you have your steam flow here. The TDS was manually controlled, and you had a given feed water TDS. And this boiler is operating all the time with a combustion efficiency of 80.5%, which just kind of comes into play in just figuring out your fuel cost or your fuel cost. And then also there's some water savings, which I'll explain. So the solution summary, we were able to install an automated blowdown control system and a blowdown heat recovery skid. So we captured the flash steam for use in the deaerator, like I mentioned before, and used the blowdown drain flow to preheat boiler makeup water. We saved a solid amount of energy and fuel, but also note that there are significant water savings, which are resulting from reduced blowdown flow, capturing the flash steam, and eliminating the tempering water that was required. So the drain of your blowdown tank is, if you have an atmospheric blowdown tank, it's at around 212 degrees. Most sewers have a temperature limit of around 140 degrees. This can vary, but that's like a common temperature limit. So most facilities will have tempering water where you're just dumping cold water in just to cool down that blowdown flow so you can get it into the sewer. So there's a lot of water being wasted there as well. And the project resulted in $44,000 of annual savings for a $120,000 project. That's a 2.7 ROI, 2.7 years ROI. That's pretty good. The next opportunity is combustion, burner combustion tuning. So combustion tuning is an opportunity at the boiler burner. And basically you're testing the flue gas and visually inspecting the flame, looking for evidence that there is too much combustion air being used in the burner. So, you know, in order to have complete combustion, you always need some excess air. You know, what's called your stoichiometric ratio is like your ideal conditions for combustion. But in the real world, you need excess air to actually get complete combustion, which is not really possible, but, you know, for all intents and purposes, complete combustion. And in some cases, you end up using way too much excess air, which cools down your flue gas and decreases the efficiency of your boiler. So you want to hit a sweet spot of just enough excess air to get complete combustion without using too much. So one thing to note here, some burners are actually designed to use too much combustion air, basically to control NOx, so NOx emissions. So just make sure you understand your emissions levels and what they're trying to do there before you just say, oh, they're at 30% excess air, I'm going to drop it down to 15 and save some energy. You might be messing them up on their emissions levels. The solutions here are combustion tuning and in some scenarios, an O2 trim system. So that's a continuously, or a system that's continuously monitoring the flue gas and checking oxygen levels and modulating the combustion air fan either through a VFD or the dampers. But kind of only really helpful if you have a lot of variable loads. So here's a table of combustion efficiency based on flue gas temperature minus combustion air temperature. And then on the column to the left, you have excess air and oxygen. So typical excess air percentage is 15%, which corresponds to 3% oxygen in the flue gas. So those are not the same thing. For the example, a natural gas boiler is operating at the following conditions. I won't read through all these, but the main one to note is they're at this 45% excess air level. That's really high for natural gas. So they're operating at 78.2% efficiency. So the solution is tune the burner, bring the excess air down to 9.5% and increase the efficiency to 83.1%. Your fuel saved is shown here. For an annual savings of $235,900, roughly $900, and that's a big savings for basically a service call. The next opportunity is stack economizers or combustion air preheaters. So this is again just capturing energy in your flue gas. Economizers are generally referred to flue gas heating your feed water going into the boiler, where combustion air preheaters is preheating your air going into the burner. Your indicators are that there is no economizer or combustion air preheater, and that your stack temperature is significantly above the steam temperature and the flue gas condensation temperature. And so you don't want to get your stack temperature down. Like for natural gas, it shows here at the bottom, it's 250 degrees is your condensation temperature. You don't want to get near that temperature, or you will be raining acidic water out of your stack and corroding your stack as well. And so you need to keep some margin above those temperatures. Efficiency solutions are to install an economizer or install a combustion air preheater. This is a large Lungstrom combustion air preheater under construction. It's pretty neat technology if you want to read about that. The background for the example is a feed water economizer is installed that reduces a boiler's flue gas temperature from 600 degrees to 400 degrees. And there are the parameters. So the solution summary is You calculate the useful energy based on your starting efficiency using this table. So this is kind of the takeaway here, is that we're able to reduce the flue gas temperature going out, which increases the efficiency from 75.4% to 80.4%. We are calculating the new amount of fuel used, and your savings is the difference between 600,000 million BTUs and this number. For an annual cost savings of $270,000. So, yeah, that's pretty good savings.
That would be about typically a 1-year payback, perhaps, on a typical system.
And this is a significant reduction in flue gas temperature, but it is realistic.
Thank you, Chase. This is James Moore. Jamie, I'm going to take over for a minute, just talking about distribution opportunities, which normally you're on your way out of the boiler plant now, and you're working your way through the facility, whether it's a hospital or an industrial facility or what have you. And you're looking beyond steam traps, but steam traps are normally where you start because those are always a high payback and a good opportunity. But they also service all the steam using equipment as well as all the drip legs. So it gives you visibility through the steam trap audit to look for everything else that might be an opportunity, which always includes insulation. And since we're talking about steam systems, we're talking about thermal insulation and normally system pressure reduction opportunities as well. So most facilities, whether it's operating on a district energy plant system, in other words, buying purchased steam that comes through into the facility and through pressure reducing stations, or it's produced in the boiler plant, typically at a high pressure of 120 to 125 PSI saturated steam. Normally you're looking to reduce that pressure for other uses and purposes within the facility. So we look for those opportunities, and those are where you're going from usually a medium to a low pressure or a high to a low pressure, and that low pressure has long runs of piping for distribution for terminal heating units. And that's where if you're especially in warmer climates, so picture a hospital in California or in Florida that has a large steam load, which they normally do, also would be potentially using steam for heat if it's an older facility. And in those cases, you have normally long runs of distribution piping, and it's 50 to 70 degrees out, but the steam is running at 15 PSI. So here's a great opportunity to put in a digital pressure reducing station to automatically reduce pressure down to 3 or 4 PSI during those warmer days when steam pressure is set for that worst day of the year. Normally, steam systems are set on a pressure and not often regulated or modulating, so that's a good opportunity. We're looking to minimize vented steam. We're looking for leaks throughout the system. We're looking for automation of distribution systems, and these are the things that you can look for throughout any type of facility normally. Returning, in this case, condensation, which we talk about on the recovery side, but this is really part of that distribution opportunity. So you're looking to maximize steam condensate return to the boiler plant, or if it's district energy, then you can pull the heat out and just return the fluid back to the district energy. So these are things that we're looking for. So steam condensate return systems might be better utilized. Instead of using electric, you can use steam as a motive force and save money there. So it's quite a bit of opportunity going through a distribution system beyond the steam trap. And this is what we want to talk a bit about today. Next slide, please. So we're going to highlight a thermal insulation as an opportunity. I'm sure everybody in this room is very familiar with insulation. but it's essentially we're talking about reducing, improving heat transfer on the surface, so you can maintain a warm, hot piping system without losing a lot of that thermal efficiency. And also, it's an important safety factor, because steam, especially above low pressure, is anywhere between 250 and 325 degrees to the touch. So oftentimes there's a safety reason to insulate piping. But indicators here would be obviously lack of piping and insulation, or degraded and insulation, and also improperly sized insulation. So you're looking for, clearly you have to look high, because it's normally up high, or it's in crawl spaces, or oftentimes it's not obvious without getting into mechanical rooms and into crawl spaces to find those opportunities, but they're usually there. And obviously there's an opportunity for improving the overall efficiency of the boilers and reducing the amount of water that you need to make up into the boiler. So ironically, insulation is a water conservation opportunity as well. Next slide, please. Efficiency solutions include conventional insulation, and that's going to be fiberglass or mineral fiber, typically on steam systems and condensate systems, and removable insulation covers that are fabricated to fit and are designed to specification based on whatever the product or the facility is that you're working in. And just some tips from Valancourt's 2001, which adds a little bit of levity to the system. But if it's already covered with asbestos, the payback period will be measured in decades. That's the key thing. When you're looking at insulation, you have to know what is asbestos and what isn't asbestos, and understand what's going to be required for remediation of that hazardous material before you offer a solution. Next slide, please. System pressure reduction, the opportunity here normally is, as I mentioned, going to be in low pressure scenarios, because typically you need to run a medium pressure steam in a hospital environment, for instance, to 60 psi goes to the sterilizers and usually to the laundry, if there is a laundry facility, which oftentimes there is. And then everything else in a hospital is generally used at low pressure. So they have to, normally a hospital is going to either buy or purchase or produce steam at 120 psi and reduce it. So the opportunity is really in that reduced steam pressure to low pressure. So that's that on that slide. And the indicators here is that your pressure is frequently higher than required, and this is kind of model out the heating days and degree days and understand the steam loads and what's required. A lot of times taking note of the fact that most often when medium pressure steam is used in a facility, they're typically converting that to hot water. So if your hot water demands require a steam at a certain pressure, you have to be careful that that's not on the low pressure side, because you couldn't disrupt that by installing a PRV. So that would be one thing to look out for there. But the potentials here are really in reducing radiant losses along those bounds of linear feet of piping. You can move on to the next slide.
Yes, I'm going to take back over here. So the end use opportunities, we're not going into these in detail. This is really based around your equipment that's using steam. So, equipment that's operating inefficiently, not to spec, and also, remotely located equipment that maybe there's an opportunity to convert to electric equipment, or possibly isolate that segment of the system, so you're not just constantly losing heat there. I did a project with a paper mill once where they at one point had 11 rolling mills and they were down to one, and their steam system was all over the place, and most of it was not being used. And even though they had isolation valves, then you have to maintain those valves. They're old valves, so they're leaking by, and you're still losing heat in those sections. And yeah, so the solution there was to go in and actually just cut and cap sections and kind of simplify their system down to just supply that one mill that they had left, or one rolling piece of equipment. So on to recovery opportunities. So this is all around condensate. You have condensate waste heat recovery, capturing high pressure condensate flash steam. And then those are the ones we're going through in detail. Obviously, condensate collection and return is always a good opportunity if possible, but we don't. So the first one, Jerry mentioned this earlier, condensate waste heat recovery. So this is kind of specific to district users. So usually any condensate that's returned to the boiler plant is carrying heat, and that heat is conserved because you just put it right back in your boiler. But for district users, they're taking steam from the district header, and then once that condensate leaves their facility, for their intents and purposes, that heat is lost. So the opportunity here is basically trying to get that condensate, all the heat out of that condensate that they can before they return it to the district plant. And so the indicators here are, one important one is that there is no temperature penalty for the returned condensate, so that's important. And then that they have high condensate return temperatures, and also an opportunity to utilize the heat that's being wasted. If they can't put it anywhere, there's no opportunity. So the efficiency solution here is basically a heat exchanger to capture heat from the condensate before returning to the district. The example here is we have a hospital utilizing district steam. They have no cost penalty for condensate return, but they are returning pretty hot condensate to the district plant. So in the same room, there's a steam-driven water heater that is heating water from 50 degrees to 150 degrees. I don't show that here, but they have a hot condensate temperature returning to the district line of 194 degrees. They're going about 104.5 GPM average flow. And the hot water heater is operating at 8.5 hours per day, 365 days a year. So that's important because, like I said, that's the only time, if that's the user that you're capturing the heat from, that's the only time you can really utilize that heat. The rest of the time when that's not operating, your condensate's still going back hot. And then they have a steam cost of 20.33 million BTUs, or dollars per million BTU. So this is a picture of the potential project. On the left here, you have a condensate tank. So this is pumping out. You can't see the pumps here, but they're pumping into the district return header. And over here is the steam-driven water heater. So you have domestic water coming in at 50 degrees. They are using steam to heat it to 150 degrees. So the solution here, there's PFD of the system, but we're installing a pump on top of the collection tank to pump water out of the collection tank through a heat exchanger to heat this domestic water, which will then go to the hot water heater. And then that condensate is then returned back to the heat or to the collection tank. And so we're actually cooling the water down from 194 degrees to around 172 degrees based on our calculations. And we are able to completely heat the domestic water from 50 degrees to the set point of 150 degrees. So effectively eliminating all of the steam used to that water heater. So here is the solution summary. Basically, the heat exchanged is your 104 This is based on our heat and mass balance that we did, but just breaking out the heat saved, you have 104 gallons per minute of condensate. You have a temperature differential of 194 to 172 final temperature in the tank, and you're getting over 1 million BTUs per hour saved. And so that number times your 8.5 hours per day times 365 days a year, you get an annual savings of 3,566 million BTUs. With this steam cost, your cost savings is $72,497 a year for a payback of 2.1 years. Next opportunity is capturing high pressure condensate flash steam. So when you're out in the plant, you have steam users, they are dropping condensate out of the system. And sometimes if that user is far enough away from the plant, you need a collection tank, which will, then you have pumps attached to that, and that will pump the condensate back to the boiler house or boiler plant. So these collection tanks are often bent to the atmosphere. So if you have a high pressure system and then you drop it into an atmospheric collection tank, you are venting a large amount of steam out of that tank, and it's just wasted. So here you have a diagram or schematic of this is two-phase flow going into the tank. Some of it is flashing to steam. Here's liquid coming into the tank. Maybe a little bit of that is flashing to steam as well as it drops pressure. So you have your steam out and your liquid out. The solution here is to install a pressurized flash tank where you can use the flash steam for your low pressure system, or possibly your deaerator, or any low pressure steam user that you have available. So this picture, you have a bunch of air heating coils. They have a condensate out that's going into the flash tank, and then the flash steam is going to the low pressure steam user. Your condensate return, you're still using that condensate just like you were before. The difference is that you're no longer losing your flash steam. And this valve here actually opens when you're not able to use that flash steam. So if the users on that low pressure system are off, the flash tank would basically vent as it did before, but at a little bit higher pressure, so still saving some lost steam. The example, you have 6,000 pounds of 145-pound condensate going to an atmospheric flash tank. So all the steam is lost. We have some steam properties here, or actually condensate properties rather. You have a 30-pound low pressure steam system, so that's available to use the flash steam. And then the current collection tank is atmospheric. So you have some liquid coming out and some steam coming out. You've got an $8 per million BTU per million BTU steam cost and 8,000 operating hours per year. So here I'll kind of go through the calc real quick, but basically what you're looking for to start with, all of your steam out of your atmospheric tank is going to be conserved. So that is your savings. So you're looking for this flash steam percentage. You can calculate that based on the enthalpy. This number right here represents a ratio of liquid condensate coming out. It's 1 minus the flash steam percentage times the liquid enthalpy. This is the flash steam percentage times the steam enthalpy. And you saw for flash steam percentage, you get 16.3%. Multiply that by the total flow, and that gives you, this part gives you your steam flow, times the enthalpy gives you your energy lost per hour. And so the energy conserved is all of that energy is conserved. Now that's not how much steam you will be flashing now. Now you're going to like a 30-pound tank, you're flashing less steam, but all that energy is conserved from the previous configuration. And so your annual savings here is roughly $72,000. And that is the last example. I'll kick it back over to John to go through the last slides, and then we can do some questions.
Yeah, hi, everyone. Let's see, we got the questions here. All right, so I might not be doing in order, but let's see. Okay, here's one. When reducing distribution pressure, is there a general rule of thumb for how far you can reduce pressure from design before considering upsizing distribution piping?
I don't know of a rule of thumb. You just have to check the velocities. So that's a good point. I think maybe I had a note on the slide there, but you know, for low pressure systems in the same amount of steam flow, your piping sometimes can be much larger, or it needs to be much larger. So you just have to check that it's within the acceptable velocities of the facility's pipe specs, or you know, recommended velocities is what I would do.
That's a tough question. So if someone wanted an answer to that, does that mean they should talk to a designer? I guess that's the answer, right?
I think so. I mean, you can calculate, if you can calculate the velocity in the pipe based on the steam flow, the pressure, the density of that pressure, that's the answer. And then, I mean, typical velocity is like 100 feet per second to 120 feet per second. Those are not maximums, but that's like what you would normally design to. So yeah, it's kind of a case by case thing. I don't know of any rule of thumb. Do you, Jamie?
No, but I think this might be specific to the idea of doing a PRV on a low pressure system. If that is what the case is, typically low pressure steam operates more efficiently at lower pressures than at higher pressure, where it's pressurized and travels less. So ironically, steam at 3 pounds is going to travel further and be more efficient in a low pressure steam system than steam at 12 pounds. So with low pressure steam systems for heating, radiant heating, ideally you're operating those at 3 pounds. So your set points are typically at 15 pounds. That's how those set points are installed when you buy and install a system typically. So the digital PRV is really set to read and automatically adjust that pressure based on outside air temp. But that does take a load calc, so you have to understand what the load is to the building and what's required, but there's no piping upsize requirement for that. To run between 15 and 3 pounds on a low pressure steam system, if that is the question, wouldn't require a redesign of the piping.
I've heard.
Yeah, I guess the important. Sorry, John.
No, go ahead.
I was just going to say, an important point there is if there is an opportunity to reduce the pressure, is generally because there is a lower load, and so your flow is lower. So hopefully it's a problem that's kind of solving itself.
So I ran into, I'm vaguely remembering this and possibly remembering it wrong, but I ran across a building with medium pressure steam. They didn't need it. They needed it only at low pressure, but if we were going to just reduce the pressure, somehow the piping was either oversized or undersized to do that, and we couldn't just reduce the pressure. Does that ring a bell? Is it a little more complicated than just reduce the pressure, everything will be fine? Aren't there problems that can happen if you do that?
Yes, from medium to low pressure, yes.
Okay, and I don't know if you, medium pressure is what range more or less in PSI, and low pressure is what range?
Medium pressure is 50 to 70 psi typically of saturated steam, and low pressure is 2 to up to 30 pounds of saturated steam. Typically is considered 15 psi.
Okay, yeah, so that's what I thought. Yeah, because that's something it's something I would do, only knowing very little. If you know a little, then you're very dangerous. And I would, be the type that would suggest to the facility owner, yeah, just reduce it. Everything's gonna be fine. And I don't think necessarily it would be fine.
No, Chase mentioned that you need to do velocity calcs to understand the steam flow through the system. But as much there as it's also dependent on how much condensate you're going to return. So it's the sizing of the condensate lines are also important in that. scenario as well.
Yeah, seems complicated. Okay, so for someone who's an M&V person who goes on site, once a year or so, just to look around and see if they can find some really easy fixes. I guess one might be they maybe if it is a large steam system, they probably should be doing a boiler combustion analysis every darn time, because that would be easy. I mean, you showed how simple it was, and it's not that difficult to adjust, and you can get a lot of savings out of that. What other really simple things can someone who's not a steam expert like you do to get a good payback, let's say?
I think that the opportunities that are sometimes obvious are if any, like the blowdown opportunities or the condensate return opportunities where you have really hot condensate being returned to the district, or if you have really hot blowdown going down the drain and a lot of tempering water. I saw another question on there, not to jump ahead, but somebody asked what's an acceptable percentage of, they said boiler makeup water. I thought they said boiler blowdown. But I was gonna say, if you have a really high blowdown, 2 to 8% is typical, but if you have a high blowdown rate, that's a easy opportunity to identify. If they're, like, we went through a bunch of these, but if they have manual blowdown configuration instead of digitally controlled, it's just things that we look for. But we see a lot of blowdown heat recovery and condensate heat recovery.
Okay, so here's one for mass balance and flow for just the steam plant. How do you calculate the DA steam consumption? Ooh, pretty detailed question.
So that a lot of times you'll do a heat and mass balance of just the deaerator itself, and so you have to balance all the enthalpies and mass flows coming in. So you have your condensate return coming in. Sometimes condensate goes right back to the boiler. Sometimes they dump it into the deaerator. You have your steam flow coming in to the deaerator. You have your boiler feed water going out. You have your makeup water coming in, which does have some heat, even at 50 degrees. Everything theoretically has some heat, right? And so it's just its own little mass balance there. And you just basically solve, you have all your enthalpies, all your mass flows, and you're solving for your mass flow of steam.
Okay, so let's see, I'm going to ask you, I mean, this is more of an entertaining question than an informational, but it's actually somewhat useful. Steam boilers can be dangerous, right? They can blow up on you. They can, like, I've seen pictures where the shell would blow up and the cap at the end of the boiler would like blow through the wall into the parking lot and stuff like that. Now, I already know the answer to this question because I took a steam operators course once, but I thought it'd be interesting. How do you blow up a boiler? Not that these people want to, they don't. They want to make sure they never blow up a boiler, but how does one go about blowing up a boiler?
There's so many safeties on a boiler. You really have to be kind of bypassing a safety system, I would say, is the easiest way. So if your relief valve is clogged, I don't know if this is a rumor or not, but my understanding is that the first boiler that ever exploded was a locomotive where the guy that was shoveling coal into the furnace got, the relief valve was going off and it was whistling, and he didn't like the sound, so he shoved a rag into it to
Nice.
muffle the sound, blew the locomotive up. Now, they didn't have the safeties we have now, but I think that most boiler failures happen due to operator error.
Oh yeah, certainly. So I think what I remember was if for some reason the amount of water in the boiler goes way down, I don't know why, but the water coming in, there wasn't a lot, and all this, and you realize, oh, the water's low, let's fill it up, and then you add all this water to the boiler, and then the water flashes to steam, and then you get that's a quick way to fill up the boiler.
Yeah. The most dangerous situation I ever encountered with a boiler was it was a big 1400 psi power boiler. The boiler manufacturer had decided to build their own manway. So instead of buying a pre-made manhole, they designed it themselves to save some money. And those manholes are typically like double hinged so that you can seat them evenly, if that makes sense, instead of like a swinging door. And they didn't do that. So they had a swinging door manway. The gasket got pinched on one side. And then when we were testing the boiler, we got it up to about 400 pounds and the gasket blew out. And it literally, there was a guy testing the boiler. He had went somewhere else, but his laptop was there. He had been there 30 seconds before. And the steam melted his laptop, filled the whole boiler house with steam. Which I learned then that actually some of the danger there is you can die from asphyxiation. So the guys that were up on the upper level had to rush out of the building. But that's not something anybody would ever really run into, kind of an obscure problem. But yeah, they definitely are dangerous if you're not operating in them correctly or not designing them correctly.
Let's see.
Gentlemen, can we slide forward 2 slides to the email address on the screen?
Okay, yeah, I'm gonna ask one more question. So do we need to meter the steam flow into the deaerator tank? Another question. You guys got an answer to that one?
I mean, you can, yeah.
Yeah, we don't know the context of that question. Meter it for what? If you're doing for M&V, for trying to track energy savings, I don't think so.
Yeah, that's not normally something that we're messing with as far as like an efficiency solution. It's kind of just like the plant design. I mean, I know it costs money, but in my opinion, I like to know what all the flows are. So it's just kind of like, why do you need to know, or is it important to you?
It says, for the mass. Okay, so back to that. So do we need to meter the steam flow into the deaerator tank for the mass balance equation? That's the whole question.
You have to have, it's kind of one of those equations where you can only have so many unknowns, right? So if you know your makeup water flow and your boiler flow, your boiler feed water flow and your condensate return, then you can calculate your steam flow. If you're meeting your steam flow, you can calculate a different flow, but you can back the flow, but it's
That's good. Hey, you guys, thank you very much for coming. So Tyler, can you show there's a slide where if they want to contact them? Well, you guys, if you want to contact James and Chase for some reason, you might, because you might have some questions about your steam systems, or maybe you want them to help you with something. You can always contact us at webinars@abraxasenergy.com, and we'll pass it on. Hey, thanks, guys. Thanks, James. Thanks, Chase. Thanks, everyone, for showing up.
Yeah.
We'll see you next month.